To introduce Dr. Preetum Nakkiran, today's speaker in TAMIDS speaker series. Dr. Nakkiran is a research scientist at Apple in the machine learning research group. He builds conceptual models for understanding learning systems, including deep learning. And his presentation today is on deep bootstrap framework. He does both theory and experiments, and he also works on distributional generalization and deep double descent. And Dr. Nakkiran has a PhD in computer science from Harvard, and he was advised by Bose, Barak, and Madhusudan. And during his PhD, he co-founded the Harvard ML Foundations Group and co-ran the corresponding seminar series. He did his postdoc at UC San Diego with Misha Belkin's group, and it was part of NSF-Simmons collaboration and the theoretical foundations of deep learning. He has also worked with Google Research and OpenAI, and is a prior recipient of Google PhD Fellowship and the NSF GRFP. Dr. Nakkiran did his undergrad work at EECS at UC Berkeley, and in his spare time, he likes to climb mountains and do camping. But today he'll have less of a mountain to climb as it's familiar territory for him. So over to him on this talk, the deep bootstrap framework. Take it away, Preetum.
Thanks a lot for the introduction, and thanks for inviting me here to this seminar. It's my first time in College Station. I'm excited to be here. Let me know if you can't hear me or if there's anything unclear. I like to keep my presentations very interactive. So there's a lot of time for questions, and I want to be able to take advantage of that, especially since it's a smaller group. We can have a conversation. So I'll be talking about this paper, the deep bootstrap framework. This is some work I did when I was a grad student, and it's published in iClear 2021. In this paper, we give a new approach to think about generalization in deep learning, which I'll explain. But first, the motivation for this work, and for most of my work, is to understand deep learning. So what do I mean by understand? What do I mean by deep learning, first of all? Well, I think about deep learning as a system that accepts some inputs and produces some outputs. And the inputs to this system are all of the design choices that we have in deep learning. So the choice of architecture, the choice of initialization scheme, the choice of data set that we train on, the choice of loss function that we use, the activation function that we use in the architecture, the particular optimizer, SGD or ADAM or whatever, the learning rate of that optimizer, all of these hyperparameters. So the design choices are essentially all that the designer puts into the system, everything that you specify in the code that results in the model. And then the output of the system is, of course, the trained model. This includes the weights of the model, the functional behavior of the model, the representations, and so on. So we have this system, and we want to understand this system. What do we mean by understand? Well, the simplest way to understand the system is we want to know how the inputs affect the outputs, right? So how does what we do in deep learning affect what we get? How do these different design choices we have affect the model that we get at the end? And this is an important question because advances in deep learning these days are very unpredictable. Every new advance corresponds to some new choice of input. Maybe it's a new architecture that we come up with or a new data set that we decide to train on. And we're often surprised by which of these design choices actually work in practice. So to give an example of that, for the last 20 years or so, a particular type of architecture, the convolutional neural network, dominated computer vision applications, as we know. But a couple years ago now, this new architecture, the transformer, which was initially conceived for natural language processing applications, came and now dominates vision applications. And now transformers are used in a lot of the state-of-the-art vision networks. And the point is that this was completely unexpected, even for people with deep domain expertise in the area. We didn't really expect this other architecture to come and take over convolution nets. And it was a problem both from the theory and practical perspective. So, as a theorist, we were working to try to understand ConvNets. We were trying to understand why are ConvNets so essential to vision applications. What is special about the convolutional architecture? Turns out there wasn't much special about the convolutional architecture. It wasn't necessary. It wasn't so essential. because this other architecture, the transformer, turned out to perform, even better when the data sets were large enough. So the point is that these kinds of things happen very often in deep learning, where practice shows us that certain intuitions that we have, or certain theories that we had, don't quite capture the full story. We're often surprised. So, and we could hope that a better understanding of this system will let us both understand and predict these kinds of events. So if we have some systematic understanding of why is architecture important, what is important about the architecture, that can tell us if we should expect more advances or whether this is sort of the end of the line. Okay, so to simplify the diagram on the previous page a bit, we have this map from design choices to the model, and we think of deep learning as defining this map. And now my research program is to understand deep learning, and by that I mean I want to identify structure in this map. So this map is not a random function from inputs to outputs. It has structure, and we can think of the research program as understanding deep learning as identifying increasingly strong amounts of structure on this map. So what is an example of structure? One example of structure is monotonicity. So one of the design choices we have is how large of a train set should we train on. And you could expect that this map is monotonic in the size of the train set, meaning that adding more training data should only help your performance. So that would be a very weak form of structure on this map, which you might expect. It turns out that even this weak form of structure is not true. So I have some other works on double descent, which explore the lack of monotonicity in this map. But that's just an example of one kind of structure that we might want to study and try to characterize. So in this talk, I'm going to simplify the setting a bit to talk about specifically supervised classification. So in supervised learning, as we know, the setup is as follows. There's some distribution D on inputs X and labels Y. So in image classification, in X are images and Y are the labels, the class of the image, cats, dogs, whatever. We're given IID samples from this distribution. And what we actually do is we use SGD or some variant of SGD on a neural network to minimize the train error. And then what we measure is the test error, which is just the probability that the trained model misclassifies a new example. So this is already simplifying this picture a bit. We're saying we only care about the model through its test error. This is already simplification because we might care about things like the representation of the model, how the model performs on different subgroups of the input. But for now, we'll just talk about the test error overall. So we'll try to understand how design choices affect the test error. Yeah, the setup there, just do a bit of if you have any other questions. Okay, so the main point of our work is we introduce a framework for generalization. So let me first explain what I mean by a generalization framework. This is a bit of a non-standard view, but I claim a generalization framework is a way of factorizing this map from design choices to test. So to give an example, there's this classical uniform convergence framework of generalization. Uniform convergence says that if your design choices are restricted in a way that that satisfies uniform convergence, which means that for all models in the family, you're guaranteed that the train error is close to the test error. That is what uniform convergence says. If you're using a learning algorithm that satisfies this, you get this guarantee. And I want to think of that guarantee as giving a factorization of this map. It means that if you have uniform convergence, then the effect of design choices on test error factors through their effect on train error. Meaning that if you want to know how the design choices affect the test error, it's enough to know how design choices affect the train error. And then uniform convergence will tell you that the train error implies a certain bound on the test error. Right? So in other words, uniform convergence says that whatever you do on the train set is exactly what you get on the test set. And so if you want to understand test behavior, it's sufficient to understand the training behavior. So I'm expressing this as a factorization of this diagram in sort of the category theoretic sense of factorizing. But is this schematic clear? Like I'm saying that this arrow, it can be equivalently represented by this factorization. So it's like you can think of the trainer as like a sufficient statistic for the test error in the setting. It's all you need to know the test error. Okay, so the uniform convergence framework says that you should focus on this object, the train error. But as we know, this framework doesn't apply to deep learning because this diagram doesn't factorize for deep networks. Specifically, we know that in deep learning, any network that's big enough can reach zero train error, but they could have vastly different test errors. So this means this diagram doesn't factorize. The train error does not imply a bound on the test error because the train error can be zero even with vastly different test errors. So in other words, the uniform convergence framework does not explain deep learning because it does not provide a valid factorization. So in our work, we'll present a different factorization that I claim does hold empirically for deep networks. So instead of the train error being a sufficient statistic, I'll give you some other object that I claim is sufficient to understand test error. Okay, so now that's sort of the background, the context of the result. I'll now explain the framework itself. And the main idea in the framework is to compare what we call the real world to the ideal world. And I will define these two worlds now. So let's consider a fixed learning setting. So we fix a distribution on inputs and labels. We fix a certain architecture, and we fix a number of samples. And given these objects, I'll define the real world as essentially training a neural network of this architecture on this many samples for t time steps. So explicitly, the real world as a function of n trained samples and t time steps is defined by the following thing. You first sample n samples from the distribution. Then you initialize an architecture from the family. And then for t steps, you take t SGD steps, meaning at each step, you sample a mini batch of samples from the train set, take a gradient step on the mini batch with respect to your loss, and then output the model at the end. So the real world corresponds to exactly what you do when training a neural network in practice. You take a finite train set and you iterate through it for multiple steps, and then finally output the model. Now in the ideal world, the real world sort of corresponds to taking your train set and looping through it multiple times, and finally outputting the model. Now in the ideal world, we do the exact same thing, but on fresh samples at each time step. So we imagine that we had some distribution D, and imagine that we actually had an infinite number of samples for this data. You just push a button and get new samples. And now we do the exact same thing of training a neural network, but instead of reusing samples from a finite train set, every time we take a gradient step, we just go and collect fresh samples from the distribution. So this is in the online optimization setting, in other words. So let me define it more precisely. So we do the exact same thing. So the ideal world for t time steps, we do the exact same thing. We take an architecture from the family, and then for t steps, we sample a mini batch, but now from the actual distribution itself, not from a finite train set. Then we take a gradient step on the mini batch and we repeat for t steps and finally output the model. So again, these worlds are identical in all aspects, except how we sample a batch. Right? In the real world, we sample a batch from a finite train set. In the ideal world, we sample it from the true distribution itself. Are there other kind of differences between, like, are these definitions clear? So the ideal world, by the way, sometimes we actually do this ideal world. Sometimes if we're operating in settings where we have a lot of data, then sometimes we actually just go through the data in one pass. And the one epoch setting is exactly the ideal world. Whereas the real world is multiple epochs. Yeah.
So why is this an ideal world if you're not characterizing what how you're sampling the data or exploiting like locality patterns or like temporal patterns in the data set, which could help the learning?
Oh yeah, right. So this may not be the ideal way to learn. That's a good point. It's ideal for me because it satisfies some theoretical properties that the real world does not. So I'll get into that. So specifically, what is surprising about, like, what is the missing ingredient for understanding generalization in deep learning? It's that we train on the empirical loss, but we care about the population loss. So we train to minimize the train error, but we actually care about getting a small value of test error. And the mystery is how do we connect these two components, the train error to the test error. But in the ideal world, this is no longer a mystery because there's no train set. We're actually directly optimizing on the quantity that we care about. So because the ideal world corresponds to SGD truly on the population loss. So the point is it's ideal because this is running SGD in the setting that it was invented to run for. It's running SGD on the population loss. So to elaborate a bit, we can imagine that we have some true population loss function, and we're given stochastic gradient access to this loss function. And so if you're in the setting, what you do, well, you just run SGD. You keep doing gradient oracle calls, and you descend on the loss. And that's a theoretically principled thing to do. Right. So the point is, I'm calling it ideal because it's a theoretically principled setting. Running the ideal world for longer can provably improve your test loss in a way that running the real world for longer does not. We don't have any guarantees on running the real world. Yeah.
So how are these even comparable if the metric that you're using is different?
Oh, sorry, the metric is the same. So in the end, they output two models. They output a model in each world. And now my main claim is that the test error of these two worlds are going to be close. So I'm comparing them under the same metric, which is test error.
But in one of them, the test error is approximated with in the real world, your test error is approximated with the sample. And you're saying in the ideal world, you actually get the distribution.
Oh yeah, so sorry. In the real world, you always evaluate the models that you get with respect to the true test loss on the distribution. I should clarify that. Yeah, so both of these worlds output models, and then you're going to evaluate these models in the same way. And I'm claiming that the test performance of these models are very close, even though the worlds themselves are very different. One is doing a finite sample optimization, and the other is doing a sort of online optimization. So if you don't look into these boxes, then the test error is closed. And I'll phrase this claim more formally. But yeah, this the talk will depend on using these two worlds. So yeah, please do continue asking questions about this. Yeah, so everything really is identical. For example, if we sample a mini batch of a certain batch size in the real world, then we want to use the exact same batch size in the ideal world. So everything is the same. You know, you can think of it as in your training code, you just change the data loader, right, to samples from the distribution instead of sampling the train set. That's exactly the change I want to make. And it's very important that you train for the exact number of total steps in both of them. That's what we're comparing. Now let me show you an experiment, and then I'll make the claim more formal. For intuition. So here we're training an MLP in the two worlds, the real world and the ideal world. This is going to be in an image classification setting similar to CFAR, but a setting where we have a lot of samples, and I'll describe the setting later. But so the real world is similar to CFAR, where we have 50K samples, and we train on it in 100 epochs, 100 passes. And in the corresponding ideal world, we will train on 5 million samples in just one epoch. So this corresponds to having a fresh set of samples in each epoch of the real world. Okay. So this plot shows the test performance of both of those worlds as a function of train time. So the x-axis here is the number of SGG iterations, the train time, and the y-axis is the test error, the test soft error. And the solid red line shows the test performance of this MLP in the real world. This is just the standard thing, the standard loss curve of function of iterations. The dashed red line shows the exact same model trained in the corresponding ideal world, meaning that for each of these epochs, it sees a fresh 50K sample from the distribution. And the point is that these lines are very close to each other, meaning that the ideal world performance, even though it sees these fresh samples, performs very similarly to the real world. And this holds even for other networks. So here we're training a ResNet in that same setting. It performs very well in the real world. it generalizes very well, but it also optimizes very quickly in the ideal. Yeah.
So, do you do this for multiple runs? Like, depending, as you know, like with different iterations, different random seeds, you'll get different results. So how consistent were the results across different runs?
Oh yeah, like what's the variation?
Yeah.
Yeah, that's a good question. These are plotting means over some ensemble, but the variation isn't too much between these. So they concentrate very well on these lines. Yeah, but yeah, that's a good point. That this statement is it. I'm really making a statement in expectation over all of this randomness, like the shuffle of the samples and the sampling itself. Yeah. Good question. So one kind of hint for why this is always interesting is it's suggesting that the models which generalize better in the real world, like the ResNet compared to the MLP, are also those that optimize faster in the ideal world. And I'll get into this more a bit. Yeah, it's also even for vision transformers. So specifically, in the ideal world, it's a pure optimization question, right? Where there's no generalization because there's no train set. We just see this loss function that we take SGD steps on. And so these curves, the dashed curves, can be interpreted as just the convergence speed of an optimizer without talking about generalization. Okay, now let me define the conjecture a bit more precisely. If there are any questions. Yeah.
These look the same.
Hmm?
Like, what am I supposed to take away from the dashed
Oh,
line
yeah,
and the
yeah.
solid line?
Yeah. The point is that the dashed and solid line are almost identical, but they're two very different experiments. The solid line is the real world where you're doing multiple epochs, and the dashed line is the ideal world where you're seeing fresh samples each time. So you might expect that the ideal world should do much better than the real world, right? Because you're seeing actually fresh samples in each epoch. You're seeing a lot more data potentially, so you could expect that the dash line is much better. But the sort of surprising thing is that you're not winning much by seeing fresh samples. Another way of saying this is maybe the learning method that you're using can't distinguish whether it's seeing a sample it's seen before or whether it's seeing a fresh sample. Or at least it learns a similar amount of information from each setting. But that's an intuition, that's not formal, but that's sort of how you might think of the results. Okay, let me define this a bit more formally, which will also reveal another interesting aspect of this. So let me define the stopping time, T of n, as the time it takes for the real world optimizer to converge on its train set of n samples. Well, by converge, heuristically, let me define this as reaching less than 1% training error. So now our main conjecture, which we call the deep bootstrap, is that for all times until the stopping time, the test performance, the test error in the real world is close to the test error in the ideal world. In words, we're saying that SGD on deep nets behaves similarly whether it's trained on reused samples in the real world or on fresh samples. And this similarity holds up until the time the real world has converged on its train set. So why is the stopping time important? Why doesn't this similarity hold for all time? Well, because the ideal world, you should expect it to always improve with additional training time because it's always seeing fresh samples. Whereas the real world, at some point, at some time, it will have just fit its train set entirely, and it's not getting anything more from running more iterations. So you can only expect this to hold until the real world has converged. And I'm claiming that it actually does hold until that time. It's sort of the best, it holds for as long as you can expect. So here's a experiment that illustrates the effect of this stopping time. So we're going to train a network in the ideal world, that's this dashed line, and the real world for varying sizes of train sets. So the very light green shows training the real world on just 1,000 samples. So and we stop all of these real world models at the point where they converge. So they're stopped here at the point when they reach a 1% train error. So when we only train on 1,000 samples, it stops really quickly. When we train on more samples, it takes longer to stop. But the point is that up until that stopping time, these colored lines are very close to the dashed black line. Meaning that up until the real world has fit its train set, its test performance is very similar to the ideal world. So this is a sort of an interesting kind of plot, right? Because the x-axis here is SGD iterations, but each line here will vary the size of the train set. And so this is making a connection between, it's saying that the effect of increasing the train set in the real world can be captured just by the ideal world optimization behavior, so connecting train time and number of samples. But so this is why the stopping time is important. And this picture already tells you that the ideal world could be an interesting object to study if you care about generalization aspects in the real world, because it's telling you it's one experiment that tells you the scaling behavior of many experiments. Yeah.
How do you determine the stopping time?
Yeah. So heuristically, we just said here when you reach 1% train error. But this is sort of an arbitrary number. Any small enough, you can set a loss threshold and you'll behave similarly. Okay, so now the previous conjecture was about the entire trajectory of the real world optimization. But if we only care about the test error at the point when it's converged, which is often what we do, we just care about the test error of the final model, then the conjecture simplifies as follows. It says that the final test error in the real world on n samples is close to the test error of the ideal world at the time it took to converge, right? So the ideal world at the stopping time in the real world. And why is this equation interesting? Because the left-hand side is a generalization quantity. It's about the test error in the real world. This is the object you want to understand. The right-hand side involves two quantities that are purely optimization quantities. It involves online optimization, which is knowing what the ideal world behaves like as a function of time, and offline optimization, which is just knowing the stopping time. How long does it take to converge on the size of a trained set of n samples? And so, if we believe this or can otherwise prove it, it's saying that we can reduce generalization to two questions in optimization. Now, these are still two hard questions in optimization, but they're at least different. So we could hope that we could bring different tools to bear on the right-hand side. But I think this general message is what I take away from this paper, that it's possible to understand generalization without talking about the difference between the train set and the test set as we normally do. Like the right-hand side just involves optimization quantities without comparing train set and test set. So as a framework, I said before, I'm going to introduce a factorization of this map. And this conjecture implies the following factorization. It implies that the effect of design choices on test error factors through their effect on online optimization and on offline optimization, meaning just that you need to know these two terms to determine the test error. So in the paper, we empirically verify this conjecture as we vary a number of design choices. So we'll vary the architecture, the size of the model, the size of the data, the type of optimizer used, whether we pre-train or not, and whether we use data augmentation, the type of data augmentation. Essentially, all like a number of design choices. We want to verify that this diagram, this factorization is still holds. And at a higher level, once we believe this factorization, it gives us some insight into what are good design choices. So it says that good design choices should have two features. They should optimize quickly in the online setting, meaning that when we're training on this infinite stream of samples, they should optimize quickly. And this is consistent with what people are actually doing. They're using so what would you do in this online setting if you have infinite stream of samples? You would use a very large model because there's no generalization concerns. And you would do things to improve optimization. Like you would use residual connections to make sure the gradients are well conditioned, you would maybe use pre-training as a preconditioner, things like this. So what people actually do are very consistent with this intuition that this is what we would do in this online setting. The second thing we want from good design choices is they shouldn't optimize too quickly on finite samples, because you want the stopping time to be long. That you want the real world to take a long time to fit its train set, so that you get lower and lower values of this ideal world, right? And this is somewhat in conflict with the first one, but certain things people do in practice are consistent with this. For example, using regularization will slow down your optimization. It will prevent you from fitting the train set for longer, and that helps you because it increases the stopping time. Using data augmentation also increases the stopping time because it takes longer for you to fit on an augmented data set than on the original one. And so you can think of, I claim that you can view every advance in deep learning through the effect on these two factors: the effect on online optimization and the effect on training time. And we'll do this for some advances in the second half of this talk, and we'll see how to apply the framework. Oh yeah, interestingly, so after we had these conjectures, there have been various theoretical. So we phrased this conjecture empirically, and we verified it for a number of design choices. But following that, there were a number of papers, including this one, that prove our conjectures formally in settings that are theoretically tractable, like in certain high dimension. So I thought this was fairly interesting. And this is also what you would hope, because nothing about this conjecture is really about deep networks, right? Like there's nowhere in this conjecture does this particular type of architecture appear. And so you could hope that this is a conjecture that holds more broadly for optimization models. So it's sort of suggestive for me that you can actually prove it true in certain settings. Okay, let me now present yet another way to view the conjecture that I just said, which relates more to classical theories of generalization. So the classical theory of generalization says that we should write the test error as the train error plus the generalization gap, the difference between train and test, right? And classically, we think this is useful because once we have this decomposition, we're now going to study each term individually. And this decomposition, we think, helps us understand generalization because each term individually is simpler than the final test error. So our decomposition does a similar thing in a different way. So we should write the test error as the test error in online learning, this IID test error, plus the difference between the online and the offline settings, which are called the bootstrap error. And now our claim is really just that this bootstrap error is small. Okay, but this claim it needs to be qualified because this bootstrap error depends on all of the problem parameters. It depends on the number of samples, the data set size, the architecture, train time, a priori. But we really claim that none of these parameters really matter. All that matters is the stop. So bootstrap error, we claim, is just small for all kinds of. Yeah.
Try sharing the screen now. I think we may fix the problem.
Yeah, let me try that.
Sorry, it came late.
No?
Yeah. Yes. Thank you.
Okay, great. Yeah, so this is just a different way of phrasing the results we discussed. Now here's an implication of this conjecture as it applies to scaling laws. So this is maybe interesting because there's been a lot of research into scaling laws recently, especially scaling laws of large language models, where we find that as we scale up the training data sets of these large language models, their test perplexity follows a power law. And you really want to know what the exponent of this power law is, because that tells you how well these models are going to perform as you increase the train set sizes even more. So the conjecture has a certain implication for scaling laws. To set that up, let's let L of n be the learning curve in the real world. So the test error as a function of number of samples. And let P of n be the stopping time, the time to converge on n samples. And let's let L tilde be the learning curve in the ideal world. So the test error as a function of time. Now the deep bootstrap says that these three quantities are related in the following way. And that actually implies that if all of these quantities follow power laws, which we should expect empirically, then the exponent, the power law exponent in the online learning setting is exactly it is approximately the exponent of the real world, meaning that the scaling behaviors with respect to number of samples is close to the scaling behavior with respect to amount of time. So there's sort of an interesting relation between optimization time and number of samples, which a priori might be different quantities. Okay, so this was the description of the conjecture and some implications of it. Very briefly, we validated this across a number of settings. So we need a setting where we have access to a lot of samples, and we did this in two ways. The first, we generated 5 million samples from a synthetic distribution model trained to generate samples from CIFAR-10, the generative model. So we get 5 million samples that look similar to CIFAR, but it has the advantage that we can sample from it as many times as we want. So that was sort of a synthetic setting, and then we also tested it on real images by subsampling ImageNet. So why did we subsample? Because we want a task where we have a lot more data than we actually need. Right? We want a task where the task is sort of relatively simple compared to the amount of data that we have, so that we can simulate the ideal world. Because simulating that requires fresh samples each time. So we subsampled ImageNet into a binary class, and then we use this setting. And for each of these settings, we varied a number of design choices, architectures, optimizers, and so on, testing architectures of very different types, right? So ConvNets, MLPs, to transformers. And in all of these settings, we're going to plot the final error in the real world as compared to the final error in the ideal world. And the points lying on this line mean that the ideal world and the real world are close, that the test error in these two settings are comparable. Okay, so that was a description of the validation, like of the conjecture and validations. I'll now talk about implications of this conjecture. So if you believe this, what sort of insights do you have on deep learning? Could you have? So the main thing is it gives you an alternate perspective on any generalization question. It lets you transfer a generalization question to an optimization question. So for example, the question of why do ConvNets generalize better than MLPs transfers to the optimization question. Why do ConvNets optimize faster than MLPs in this online setting? The question of why does pre-training on other data sets help generalization? It transfers into why does pre-training help optimization? And in optimization, we think of things like pre-training as a preconditioning, right? And so this could give a new perspective on thinking of pre-training as preconditioning in a formal sense. And when we do this, sometimes once we do this transfer, we can use different tools. So just to study each one in particular, we can look at the effect of pre-training. And we know pre-trained models generalize better in the real world. And so they should optimize correspondingly faster. We can do this experiment where in the solid red, we train a vision transformer from scratch. And we see that it optimizes slowly, both in the real world and in the ideal world. So the solid line is the real world performance as a function of training steps. And the dashed red line is the ideal world test error as a function of training steps. And again, these two errors are really close. So this is the model trained from scratch. And now we could pre-train that model and run the exact same experiment. And then we get those lines in blue. So the solid blue line is the pre-trained transformer in the real world. It converges very quickly and generalizes well. And then we run the pre-trained transformer in the ideal world, and it optimizes very quickly. It's an online setting, and it optimizes sort of exactly as quickly as we should expect. So, so this framework captures the effect of pre-training as well. Now, many of the mysteries still remain. Like, why does pre-training help optimization so much? This is still very open, but at least now it's a different type of question. It's just an optimization question. We can study data augmentation. So data augmentation in the ideal world corresponds to augmenting each sample once. So you sample from the distribution, you augment it, you train on that augmented sample, and then you throw it away. So there's two potential effects of any change in our framework. It could affect either the ideal world optimization speed or the real world convergence speed. And we found that the main effect of data augmentation is really to change the real world convergence speed. So it prolongs the time it takes to fit your train set, and that's why it's improving generalization. But through our framework, it suggests two properties of good data logs, right? You want good data logs to do two things. First, they shouldn't hurt your learning speed in the ideal world. So what does this mean? Basically, this means your data log samples shouldn't look too different from real samples. But if your data log is doing something really weird, then it will slow down, it'll mess up your ideal optimization. So that's an intuitive thing. The second property is it should decelerate optimization in the real world. So it should make you train for longer. So you can imagine that good, like standard data logs do this. If you use this data logs to just crop and flip your images, that shouldn't change optimization much, but it should slow the fitting down. And these were actually the exact sort of same two aspects of good data log that were proposed in the previous paper for independent reasons. So it's kind of nice that our framework is consistent with these results. There's a certain theoretical perspective that also comes out of this. So it transfers questions about implicit bias into explicit questions about optimization. So what is implicit bias? Implicit bias is saying that there are many ways to reach the same train error. Like if you train a ConvNet versus a MLP, they can both reach the same train error, but one of them will have much better test error. And it's because of something implicit in the process, because you didn't, why is it implicit? Because the explicit optimization quantities, which is the train error, are the same, whether you train a ConvNet or an MLP, but something is implicitly happening to make the test performance better. And we have a view on this, which is that we transfer this to an explicit property. If you look at just the explicit test in the ideal world, the ConvNet will optimize faster. So this is at least removing one ingredient that you need to spend. And the framework, just to illustrate, also captures the effect of learning rate. So if here the solid blue line is showing the real world learning curve, and we drop the learning rate here, and you have this sort of kink in the curve. And the same kink in the curve shows up in the ideal world. So in the ideal world, we drop the learning rate here, and again we see the same test behavior. So so in each of these experiments, I'm changing a certain knob in the real world, and I'm trying to show that that knob does the exact same thing in the ideal world. And so it's sufficient to study the ideal world. It also sheds some light on a certain thought experiment that has been puzzling for the community. So there was a thought experiment introduced in this paper by Zhang et al. In this experiment, we train a network on randomly labeled inputs. And if you do this, you can find that networks that we use in practice are actually expressive enough to fit random labels. And this is puzzling for classical theories of generalization, because you would expect that such networks have too much capacity to actually generalize well, because they can fit random data. But our work gives a different perspective on it. It says that, so classically it's a problem because the test error is much higher than the train error if you do this experiment. The test error is trivial, but the train error is 0. But in our framework, the real world test error is actually very close to the ideal world test error. Because if you do this experiment in the ideal world, you train on random inputs in the online setting, you should expect to get a terrible model. And so if you compare, like our framework says, just forget about the train error. That's really the philosophy, right? You should forget about the train error. To understand the test error, you should just think about the ideal world test error. And you get the right answer in this experiment. And finally, the framework gives us insight on a certain practical mystery. And this is actually the mystery that got me thinking about this project initially, which started sort of this effort. So here's a mystery. There's two regimes that we run deep learning in practice. The first regime is when we have effectively infinite data. So this is when we're training a language model, effectively training on scrapes of the internet. We have way more data than the model size. And when you have a billion samples, you don't have a generalization problem. You only have enough time to see each sample once. And so how do you pick architectures? Well, you want an architecture that will optimize quickly. Here, all architectures will generalize because you have a billion samples. You just want one that will optimize quickly on your setting. And the other regime is when you have data that is smaller than your model size. So like 50K samples. And here, all architectures can fit your data set, but only some of them will perform well. And so here you want to choose architectures that generalize well. And the mystery is that in practice, we use the same type of architectures for both of these regimes. We use ConvNets, we use transformers for both of these regimes. But there's very different concerns in each regime. In one of them, you want things that optimize quickly. And the other one, you want things that generalize well. And so the deep bootstrap perspective is, this is actually not a coincidence, that you should actually believe that architectures which do well in the first setting will also do well in the second setting, which are actually very different settings. Yeah, so in conclusion, the deep bootstrap reduces generalization questions to optimization questions. And our hope with this work was to help refocus attention of the community on studying online optimization aspects of deep learning. And this is especially important now because many of these modern models are actually operating in this ideal world setting, where we have so much data that we only get a chance to do one pass on it. So it can be actually practically relevant. And on a theoretical note, it connects the framework connects the overparameterized and underparameterized regimes. So I had this in my past work on double descent. If you plot the test error of a model as you increase the model size, you see these two descent regimes. So in the very beginning, as you increase the model size, your test error will drop. And then you have this sort of weird double descent regime. But after that, once the model size is large enough, increasing the size will again continue to drop the test error. And the deep bootstrap's perspective is saying that it's connecting the left-hand side and the right-hand side. Because it's saying that models which fit their train sets in the overparameterized regime behave like models which are trained on infinite data, and so are in the underparameterized regime. So it's sort of saying that these two descents are actually the same phenomenon. And at a higher philosophical level, there's many diverse choices in deep learning that seem to work. It doesn't really matter what type of architecture you use. Many types of architectures work. Many types of weird optimizers work. Every NeurIPS, there's some new kind of reformulation that's basically a deep network. It still kind of works. And we want a theory of generalization that applies equally well to all of them. You don't want a theory that's too specific to ConvNets or too specific to transformers. You want something that kind of works generically. And the deep bootstrap framework says that any choice that you expect to work for online optimization will also work for offline generalization. And this maybe makes some sense because in the online setting, it doesn't really matter what activation function you use or like what architecture. As long as you're using some architecture that is expressive enough for your family, you should expect that SGD works. So this gives some maybe intuition for that. And I speculate that this conjecture holds much more generically than deep learning. Speculate it holds for a wide family of natural optimizers, but I don't know how to formally specify that family. But there's been a lot of theoretical work that's continuing for people exploring this conjecture in formal theoretical models, and so I'm hopeful for this in the future. Yeah, thanks. That's all I have, and happy to answer questions here. Or you can also reach out to me. I hope you know.